So in this video, we're going to talk about matrices and vectors. Specifically, we'll cover vectors, definitions, operations. We'll do the same for matrices, and we'll leave the interpretation of solutions to linear systems to another video. So in the last video, we saw how to balance a chemical reaction by transferring the problem into a system of linear equations, which we can then try to solve by substitution and other techniques. So specifically, the problem is to find coefficients x1, x2, x3, x4, and more if there are more molecules, such that the total number of elements on the left-hand side is equal to the total number of elements for each element on the right-hand side. We saw how this could be turned into a system of linear equations, and then we saw how to represent a system of linear equations as a matrix times a vector equaling another vector. And today we're going to talk about these matrices and vectors in more detail. So here's our linear system of equations again, and this is a more general way to write this. So we have a left-hand side and a right-hand side. On the right-hand side, we just have numbers, and B1, B2 refer to these numbers. And on the left-hand side, we have our set of unknowns, which in this case are x1, x2, xn, all the way to xn. And we have the coefficients, a11, a12, and so on, that multiply this set of unknowns in our previous example. Right? So we can take all of our variables x1, x2, x3, all the way to xn and so on, and we can organize this into a list, which we call the vector. We call this vector x, boldfold x indicates a vector. And all of these set of coefficients, a11, a12, a21, a22, and so on, we store this into this array, which we call this matrix A. So we can write this sort of algebraically as matrix A times vector x equals another vector B. And these are the elements that we'll start studying today. So let's first talk about vectors. Vectors are simply lists of numbers or collections of numbers organized in a particular form, which we call a vector. Here we have a four-dimensional vector, which has four entries, x1, x2, x3, x4, and we lump them together and we call this vector bold font x. Right? Another way to refer to these vectors is also a 4x1 matrix, which we'll talk about shortly. Here's a 2x1 matrix, or a two-dimensional vector. In 2 dimensions, and 2 and 3 dimensions in particular, we can actually visualize these vectors as being an arrow that starts at the origin all the way to the corresponding point. So for example, x1 is the value on this axis, and x2 is the value on this axis. If we had an x3 value, for example, if it was a three-dimensional vector, we would have another axis, and we can have a three-dimensional arrow, essentially. Vectors are used all over engineering. Perhaps the most famous vectors are your standard axes in 2 or 3 dimensions. We refer to this as E1, E2, E3 here. The x-axis is usually referred to as the vector 1, 0, 0. The y-axis is referred to 0, 1, 0, and the z-axis as 0, 0, 1. Right? We'll see a few mechanics problems utilizing these vectors. We can operate in vectors much the same way as we can operate on scalar values or single values. So for example, we can define the sum of two vectors. So let's write vector A. And just as a note, when I'm writing vectors, when I'm writing with my pad in this case, or on pen or paper on the board, I'm going to put a bar on top of the letter to signify that this is a vector. The reason is it's hard for me to draw boldface font with a pencil. So let's say we have a vector A, so let's make a three-dimensional vector A1, A2, A3. And by the way, we refer to vectors organized in a column like this as column vectors. And let's say we have vector B, and we'll refer to this vector as B1, B2, B3. We can add two vectors together. Let's say call the vector Z to be equals to A plus B. And all we have to do is add these individual entries. So I'm going to write the elements of the vector Z as A1 plus b1, a2 plus b2, and a3 plus b3. And that's our new vector z. Likewise, we can multiply a vector by a scalar. Let's say we have some number. Let's call this number alpha. And let's multiply our vector a by this alpha. So the result will be alpha a1, alpha a2, alpha a3. There are many other operations that we can do with vector, and here we're covering some of them. We can transpose, or we can switch the order of rows and columns in the vector. So for example, let's say we have a 4-dimensional vector here, a vector with 4 entries, and let's say it's a column vector. When we write x superscript t for transpose, x transpose, we just turn this column vector into a row vector. This operation, you can apply this transpose to a sum of vectors. For example, here we're saying that we can sum vector x to and add to it vector y, and we can take the result and transpose, or we can do the transpose on the individual elements and then sum them. The result will be the same. Another important operation with vectors, which are used a lot of the time in engineering and physics, is the so-called dot product. So let's say we have two vectors, and these two vectors are 3-dimensional or 3x1 matrices or 3-dimensional vectors. We write the dot product between x and y as the sum of the product of their individual elements, right? And there are two ways to write this. Sometimes it's written as with the dot in between the vectors. Sometimes we also write it as x transpose y. And this basically should be understood pretty much as a definition, right? Another definition is we call two vectors orthogonal if their dot product equals to 0. Another important notion of vector is their length or their size. We can compute the length of a point or a vector by taking the square of each element, summing each element squared, and then taking the square root. If you think about this, this is often the Euclidean distance between 2 points in 3-dimensional space or 2-dimensional space, right? We write this norm or this length of a vector, we call a norm, with this double lines here next to the vector. And this is a definition. This is how we define this norm to be like that. And if you remember the definition of the dot product between two vectors, we can figure out that this is another way to write the norm of a vector, or if we take the square root of both sides, this will also be equal to x transpose x. Right? And as I mentioned, this vector can be viewed as an Euclidean distance. So for example, if we take two vectors x and y and subtract them and take the norm of the subtraction, we are essentially computing the distance between the point x and the point y, or the point where the arrow is located. If we just take the norm of this vector, then we're computing the distance between the endpoint and the origin. Likewise, I'd like to mention some geometric properties of these vectors, and one of them is the so-called angle between two vectors. So if we have two vectors, right, in two or three dimensions, let's say in 2 dimensions here, I'm going to draw two vectors very quickly. Let's say that here we have vector x, and let's say here we have vector y. The angle between these two vectors, which we call theta, can be retrieved via this cosine of the angle formula, meaning you take the dot product between these two vectors, divide them by their lengths, and that will be equal to the cosine of the angle between them. If we would like to retrieve the angle, we apply the inverse cosine function. With that in mind, we can also go ahead and define what we call linearly dependent vectors. And let's say we have multiple vectors. Now we're going to, let's say, create a collection of vectors, x1, x2. These are two different vectors, x3, and let's say all the way to xn. We call these vectors linearly dependent if I can single out one of them. For example, I'll take out x3, and I can multiply each vector by a coefficient, x1 plus alpha 2 x2. And so let's say I'm going to single out now x3 and put it on this other side. So I'll have alpha 4 x4 plus all the way to alpha n xn. And let's say this is going to be equal to, I took out x3. If there exists alpha 1, alpha 2, alpha 4, and so on, all the way to alpha n, such that this side can be made to equal to this side, we call these vectors linearly dependent, meaning x3 here, for example, is dependent on the other vectors. I can write essentially vector x3 as a so-called linear combination of the other vectors. This is good to understand this graphically as well, so let's draw again two vectors in 2 dimensions. So let's say we have vector here y, and here we have vector x. If we only have these two vectors, we can talk about x being linearly independent of y, or vice versa. But let's say now we have another vector z here. Now we can multiply x and multiply y by the appropriate coefficients and sum them together to get z. So we can say that z is linearly dependent on the set of vectors x and y in this case. Conversely, we can talk about linearly independent vectors, and that's the same business, meaning if I have a set of vectors x1, x2, x3, for example, if it's impossible for me to write alpha 1 x1 plus alpha 2 x2 to be equal to some x3, and of course I can repeat this by singling out any other vector that I would like. Here I put x3 to this side. I could have put x1 or x2. The point being is that if it's not possible to find alpha 1 and alpha 2 such that this is true, then the vectors are called linearly independent, right? So these are just two definitions. When you hear these words, this is what it means. So now let's move on to matrices and talk about the differences between a matrix and a vector. Matrix typically, right, we reserve, or when we just hear the word matrix, typically this means an array, right? An array with entries both in the horizontal and the vertical direction, right? So we have here a matrix A, and I apologize for this. Typically we write matrices with the capital letter, so I'm going to do that here as well. So matrix A is written like that, and we refer to the individual elements with a specific numbering system, right? If I go, the first coordinate refers to the row, and the second coordinate refers to the column of these numbers. This is to differentiate it by a vector. This is to differentiate it from a vector, which is typically speaking just a column or a row, right? So this is a row vector. This is a column vector. So here we can talk about matrices having dimensions or sizes, right? So in this case, we see that we have 1, 2, 3 rows. So we say with this and 2 columns, 1, 2. So we say that this is a 3 by 2. The dimensions are size 3 by 2, meaning 3 rows and 2 columns. And the entries of this matrix are referred also to in a particular way, where again the first number, the first index refers to the row, so 2, 1, so this refers to 1, 2, so here's the value, and first, so that's -7, and sorry, 2, 1, right? So and 1, 2 is the opposite, so we have first row, second column, so that's 9. So this is just a standardized nomenclature. Of course, we could have chosen to define the other way around, but it doesn't matter which way you choose, as long as you choose one and you stick with it. So in all of the linear algebra books that you see matrices referred to and indexed this particular way. So there is another operation. Just like we can transpose a vector, we can also transpose a row. And the idea is the same. Everything that was a column before becomes a row, and everything that was a row becomes a vector. So, we write, just like in the vector case, we write A transpose to be the transpose of A, right? So let's compute the transpose of A in this case. So A transpose here will be equal to, now everything that was a column becomes a row and vice versa. So we can write this row by row. So 9, 3, minus 8, and minus 1, 2, and 7. And this has become our transpose, right? So if we have B to be this, essentially this row vector, then the B transpose would be 1, 2, 3. These definitions are important to keep track of because we're going to start multiplying matrices and vectors pretty soon, and we have to multiply matrices and vectors of the right sizes, otherwise things don't quite make sense. So we can talk about a matrix as being as also having operations. We can talk about operations such as addition and subtraction, right? So all that happens when we do this is we go element by element and we add or subtract them with the same elements, right? So we can add to matrix, and the addition of matrices is both commutative and associative, right? So for example, if we have A plus B, this result will be the same as B plus A. And likewise, if we have, let's say, A plus B plus C, but we decide to take A and B first and then add C, this is equal to A plus B plus C. So we can do this other way around. And of course, to add two matrices, we have to have that these matrices have to have the same size pretty much. So we can talk also about multiplication of two matrices, right? So here we're going to talk about a matrix A times matrix B, and we're going to store the result into matrix C. And there's a particular definition that we always use, so we're going to stick to this as well, which is essentially here is the summary of it, right? That we take the first row and multiply by the second column of the second matrix. Sorry, the first row multiplied by the first column of the second matrix, and we store that in the value C11, right? And we take again the first row multiplied by the second column of the second matrix, and we call that value C12. We then move on to the second row multiplied by the first column, that goes into C21, and so on. So we can write, right? So for example, C11 in this case will be A11 times B11 plus A12 times B21, right? So let's look at C12 here, and that will be equal to A11 times B12 plus A12 times B22. Like, let's do one more example here. Let's look at C21. So C21 will be equal to A21 times B11 plus A22 times B21, right? And so on. So here we have a summary of how this can be written in a more general mathematical formula. So we can go ahead and compute, for example, here's another example. We have matrix A and matrix B, and we're going to multiply these two matrices. And the question here is, what is the size of C? Well, of course, we have first row multiplies with the first column, second row multiplies with the second column, and there is no other result for this, right? So in this case, the result will be C will be a 2x1 vector, 2x1 matrix, right? And the way to compute this very quickly is like you can notice that the inner dimensions of this multiplication is 3 and cancels out this 3, and you end up with the results of the outside indices, right? So this is a quick trick to do all that. And here are the computations that you will have to do to actually compute the values, right? So you have, we have the value 3 multiplied by 1, 2 multiplied by 4, minus 7 multiplied by minus 1. You sum all of that up, you get 18, and you do that same thing for the second row of this C vector, and you get minus 6. So the last thing I'll say here is that there is just the rules for multiplication matrices are pretty much the same as scalars, with one big exception in that we cannot switch the order of multiplication. If these A and B's were simple numbers, we can always switch the order. But when it's the case of matrices, this is not the case. So we can't switch the order. This is not the same as the other one. However, the association works and the distribution also works in this operation.